Hello, everyone. Welcome to the presentation for our ICN paper, NDN-MPS, supporting multi-party authentication over NDN. This is work done by me, Siqi, and Lixia from UCLA, and Randy Kim from Operant network. So let's get started. Let's first talk about the multi-party authentication. The business model keeps evolving, and today's decision-making usually require participants from multiple parties rather than a single party. This is for better security and for also better availability. And here is a real problem we met in a solar energy network system where we want to update the solar energy inverter software. But this operation will need three parties approval as shown in the picture. The first party is the site owner because the update will let the solar system temporarily down and will affect the production. So the site owner must approve this. And the second, the operation team for the same reason. And third, we also need the approval from the quality assurance because the quality assurance or QA from the manufacturer, they need to ensure the new release is safe to use in the production and has meet all the requirements. As you can see, this already departs from the existing trust model. In the existing trust model, we have a producer, which is also the signer, who produce and sign the data. And we also have a consumer, which will verify the data against the producer's certificate. However, in the new trust model, we have third-party signers who are not the content provider. Like I mentioned, the QA team and the site operation team. The consumer will need to also verify the data against a list of signers instead of a single signer. And we also need some coordination mechanism among the signers to let them sign the same piece of data. So let's first talk about the crypto. There are existing schemes like RSA or the elliptic curve-based DSA. And we're using these conventional solutions, schemes. The solution is to obtain a list of signatures from individual signers. And when the command needs to be verified, the producer needs to present this list of signatures. But this has several drawbacks. First, it requires large packet and signature size. The space complexity is big O(n), where n is the number of signers. And also for the consumer to verify this list of packets, it requires a long verification time. The time complexity is also big O(n), where n is the number of signers, which is also the number of packets. And in contrast, there is a new, not new even, there's another crypto scheme called multi-signature. So multi-signature, the basic idea is that the multiple signatures can be aggregated into a single one. So this will bring several benefits. First, there is a single signature instead of a list of packets and signatures. So the space complexity becomes O(1), and it also only requires a single one verification operation for the consumer to verify the whole aggregated packet. So the time complexity for the verification operation is also big O(1), and the main idea is realized in this picture, where you can see instead of using individual signatures, these signatures can be merged into one, this yellow multi-signature, and put it into the data packet. So as you can see, we definitely like multi-signature, and we want to go with it in our solution. Okay, so back to the support of multi-party authentication. What is missing? So first, we introduced new signers, so we need trust schema for each signer to verify the producer, and also for the producer to verify these signers. And second, we need multi-party trust schema. So this schema is to define the signing and verification rules that involves multiple signers. So this is very different from the existing ones because in the existing trust schema, there is only one signer for each signature. But here, each signature has multiple signers and also can be multiple trust anchors because they come from different organizations. For example, in our example, some signers are from the site, solar site. Some signers are from external party, like the manufacturer. And then we also need the multi-signature encoding to encode the signature and its multi-party specific signature information into the packet. And last, we need a coordination mechanism for the signers to jointly send the packet and to aggregate the signatures from individual signers into a single one. And as you can see, the first challenge can be addressed by the existing trust schema, because the verification between the signer and the producer can still using the single sign signature, which can be RC or ECDSA. But the rest three challenges are new, and we want to solve them in this work. So let's take a look of our NDN-MPS, the toolkit for multi-signature based multi-party authentication. And this toolkit contains three main parts. The first part is the multi-signature trust schema support, and this includes the new syntax for the multi-signature and the parser and the encoder of the trust schema. And the second part is an NDN-compatible multi-signature encoding mechanism, where we can encode the signature and the signature info into packet. And the third part is that we propose two coordination mechanisms for the multi-signature generation. And one approach is based on a remote procedure called RPC, and the second approach is based on NDN sync. So after having these three components, the whole process of multi-party authentication is visualized in this picture, where you can see the producer collects the signatures from the senders and aggregate them into a single packet with a packet info packet. I will explain this later. And the verifier will verify this packet against the multi-party trust schema. So let's take a look of the multi-signature trust schema. So we made several changes. The first change is that instead of having one expected key pattern of the sending key, we have a list of required sender identities, as shown in this picture. For the data site inverter firmware update, it requires 3 signatures, and the all of field in this picture, it lists the expected name pattern of the sending key. And there are also a known signer field, which contains the trust chains from these identities to their trust anchors. So this is like the trust anchor fields in the existing trust schema. And we also support the threshold policy. So the threshold policy is like a signature is only valid when key out of key senders have sent this packet, have sent this object. And we support this threshold policy with a system approach in the trust schema, where we have the at least the number field and from field. So these two fields combined together can support this threshold policy. So let me give an example. So in the picture here, for the packet site operation command shutdown, it requires first a signer. First, it requires the owner signer. So let's dive into the details. The first part is the multi-signature trust schema. We made several changes. The first change is that instead of having one expected signing key pattern, we have a list of required signer identities key pattern. As shown in the picture, for the data site inverter firmware update, this is the data name. Instead of requires 1 key, it requires 3 keys. And these 3 keys are name patterns instead of specific key names. So it first requires the manufacturer QA team's key. It also requires the operation team member's key, and it also requires the owner team's key. And we also need to include the certificate chains from the sender's key to the trust anchors. And this information are kept in the known sender field, as shown in the picture. And we also support the threshold policy. The threshold policy says that signature is valid when key out of n senders have sent this object. And we support this policy with a system approach by having at least the number field and a from field in the multi-signature trust schema, as shown in this picture. So this command, whose name is site operation command shutdown, also requires three senders. The first one is always required, which is the site owner. But the rest of the signatures are more or less in a threshold manner, where in the from field there are 4 managers, and to make the signature valid, any 2 of these 4 managers can join the signing process. So notice that we didn't use any additional cryptographic primitives like dedicated multi-signature for threshold or the Schema secret sharing. So this improves the simplicity of the whole system because we don't need to have the specific key setup and the key management for those new cryptographic keys. Okay, so the next part is about the multi-signature encoding. First, we need to have a new signature tab. This is trivial, just add a new tab into the NDN-enabled. And the non-trivial part is that we also need a new key locator to keep the information of multiple signers. And there are several requirements. First, the key locator must be consistent among all the signers so that we can ensure the signers are signing the same thing and their signature can be aggregated together to the same piece of data. And second, it must tolerate changes of the signer list during the coordination. This sounds complicated, and let me give an example. Let's say we have a policy that requires a signer from the site owner something, key something. And the producer first decides to go with the Alice, owner Alice. However, it turns out that Alice is now unavailable. So the producer needs to change to site owner Bob. And we need to ensure that this change won't affect the other signers who has already started the signing process. And to solve this problem, we use another layer of indirection and introduce this so-called placeholder key locator. And this key locator at the time of coordination is just a name. This name can be decided by the producer in whatever way it is needed. And after the signature has been collected and the signing process has been finalized, the producer can generate a data packet under this placeholder name. And this data packet will contain all the signature information. And actually, this brings several benefits. First, it allows the change of the signer list during the coordination. And second, it allows more space. The last part is the multi-party signing coordination. And first, let's figure out what is needed for this step. First, we need the producer to publish its on-site data object to all the signers. Second, we need to collect the signature pieces from the signers. And there are also security objectives. First, we need to ensure the authenticity of this whole process so that everyone is sending the right data, the producer is fetching the right signature. And second, we also want to ensure the confidentiality of the process because in the traditional producer and consumer trust model, the content is actually not available to the network until it's published. And we want to achieve the same level of confidentiality. The content to be signed should not be available until the packet is finalized or is signed. So the first approach is based on RPC, remote procedure call. I will skip the details because of the time, but here are some high-level ideas. First, we have the Diffie-Hellman key exchange in the first round trip to negotiate some keys to ensure the confidentiality of the following exchanges. The second, the result fetching is asynchronous. So we let the signer to inform the producer the estimated processing time so that the producer don't need to fetch it or keep trying fetching the data. It can wait for some time and then fetch the result back. And this approach is also repo friendly, which means both parameter and result can be published to repos. And we do this by encrypting and encapsulating the parameter content and result into a wrapper packet and name it under a way that it can be fetched from repos. And the second approach is based on NDN sync. Here we have some requirements for the security purpose. First, we need the group level encryption to ensure the confidentiality. Second, we require that there is a group identity management so that an arbitrary party cannot just join the party and know what is going on in the sync group. So okay, now we have two approaches, the sync-based and RPC-based. And the selection of the approach should be based on the specific application scenario. So let's say if the application is already using the sync protocol for other purpose, they can choose the sync-based coordination. Otherwise, if the application wants to avoid the complexity of sync group setup and maintenance, they can go with the RPC-based approach. We also implemented a C++ prototype library with some usable APIs. and this library works over the NDN-enabled library. And then in this prototype implementation, we choose the BLI signature because it requires no interactive key setup. And we have also we have also exercised this this library into NDN cert to develop a multi-party approved identity verification challenge. Now we also have evaluated the performance with different sizes of data and standard site of our library, and we confirmed that the big O1 complexity of both standing and verification time and the signature size. And that's all for my presentation. Thank you.